Hey all, my name is Artyom, and this is part 2 of ray tracing in OCaml, where I will focus on 3D vectors and operators on them, and we'll also set up this 3D scene in the virtual ray tracing space. All right, so just to remind you what we have done last time, we have set the project, and basically we have defined a couple structs here, like a structure for the pixel and the image, and yeah, there's a formatter to output the image in the ppm format, which is plain text, so it's really easy to work with. And we have defined this function called sample image, which produces this sort of gradient. And the fun part here is that as we change the code, the image will get regenerated and updated in real time. So that's very handy. Now, as for the goal of this video, I will work through chapters 3 and 4 of this book. So this the VAC3 class, where the author defines a vector with 3 elements, and then it uses it to kind of model points in 3D space and also colors with values ranging like from 0 to 1 for red, green, and blue. And so this is kind of the utility part. And the interesting part is this thing about rays and the camera and sort of the viewport and whatnot, where basically we will be setting up this scene in 3D space with the camera and the viewport, and the camera looking at the viewport, and the viewport will get discretized, and we will have kind of a bunch of pixels in the viewport. We will calculate coordinates for each of the pixels, and then we will be sending rays to these pixels, so to say. For now, the function that will calculate the color of a pixel will just be a stub, basically. No actual ray tracing will happen, but I mean, that's still an improvement over what we have right now. And as a result, we should be able to produce this blue to white gradient depending on the y coordinate. Okay, so with that said, let's get back to the VAC3 and try to implement something similar in OCaml. Okay, cool. So let's go back to race, and I will close it for now. So here the author uses kind of an array with 3 elements. We can as well use a tuple, so let's do this. Sorry, not a class. So we need a struct, and I will call it VAC3D. This will mean that it's like a 3 element vector of doubles. Oh my god, I need more coffee. And here, let's say our type will be just a tuple of floats. Whoa, hold on a minute. So here we use a tuple of 3 floats to represent 3D vectors. But is it really the best option or the most efficient option? And so the ideal scenario would be that, we need 3 floats and they take 3 words of memory, so 3 64-bit words, and they really lie, really close in memory, one next to the other. That would be the most efficient option. So in OCaml, values get boxed, some values get boxed, and if you haven't seen, I have another video about memory representation of values in OCaml, where I kind of dive deeper into how ints and floats and other types of objects are represented. But the thing is, so here we have a tuple. So how much memory do you expect it will actually take to store these 3 floats? And we don't actually need to guess. We can just fire up utop and let's create a tuple with, let's say 0, 1, 2. And now we can use functions from module obj to see how much memory it takes. So the number of reachable words for a tuple of 3 floats is gonna be, drumroll, 10 words, which is really a lot. Because also, if we do kind of the same thing for a single float, it's gonna be 2 words. Again, link to the video why this is like that. But the bottom line is, this is not very efficient. Instead of 3 words, we have 10 words, and we have, some indirection in memory, which is not very efficient. However, let's say we change this a little bit. Oh, come on. And so instead of a tuple, we just create an array. And when we do it like that, it will take just 4 words, which is so much better. And this is because there is a special optimization in the runtime where an array of floats is represented in a special way, so that all the floats are neatly packed next to each other. And this is like, as a special snowflake in the runtime. But as you can see here, it actually makes things much more compact and efficient. However, when it comes to arrays, the array is not kind of fixed in size, while with tuple we know that it, the size is 3, no more, no less. So we will keep using tuples, in the for the rest of the video, just because of some kind of extra ergonomics. But overall, this is not the best representation of 3D vectors that you can come up with in OCaml. So what do we have here? There's this kind of X, Y, and Z functions. Unary minus, indexing operators. Okay, so let's implement the addition operator. And for this, I guess like the one thing to notice here is that, so in C++, when you have this sort of operators, you can just write the code, you can use these operators, and the compiler will disambiguate the operator based on the type of the left-hand side and the right-hand side, and will use the right operator. In OCaml, there is no type-based disambiguation. So although we will define these binary operators and unary operators, it will not be automatically involved. But we can get pretty far with creative use of local opens, I think. So let's define the operators and see how it goes. So that's gonna just sum up 2 vectors. Okay. And we need to do the same thing for the for other operators as well. So let's say let's define the minus. Okay. Now let's define the operator multiply, which will do scalar multiplication. So it will look something like this. We will have the multiplication, and then we will have the kind of scalar value a, and we'll have the vector. Now this is something that is a bit questionable, in the sense that why do we use the multiplication operator for scalar multiplication rather than, let's say, something like a dot product or a cross product of vectors? No good answer here. I guess we'll just I think it will just look more natural when we try to actually work with these vectors, but we can always revise this, so it's not a biggie. Okay. Now that we have a bunch of operators, let's also define this thing called length and length squared. And just length. All right, we may probably need some more operators later on. But for now, let's just kind of fast forward a bit. And so here we have another thing called kind of the color utility function, which basically translates from this representation of color where we use just a double value from 0 to 1 to 0 to 255. So let's do the let's implement the color as well. The color is basically this vector, but with an extra function inside. And we already have this thing called pixel, which is this kind of representation of a color with an integral value from 0 to 255. So let's call this function to pixel. And we can just include vector 3D here. And so here we have this factor. Then multiply using our operators. So we could do so RGB are just floats here, and this works because t in this case is just a a tuple, so we can easily deconstruct it like this. And now we can just create a pixel. All right, looking good. Okay, so the next thing is the ray class. And so what we have here is basically a ray is just a thing with an origin, which is a 0.3, and a direction, which is just vector 3. And for now, we can just define this 0.3 as a basically an alias. This will not give us any extra type safety, but we can try maybe to dial this in a little bit further down the line. But for now, let's define the array. Okay, so we need the type definition, and this is going to be origin and the direction. Okay. Now we have this function here called at, which kind of takes this scaling, as we see here, and just scales this vector along its direction axis. So let's do it. And here we again can use these operators that we have defined above. If we try to do it just like this, so origin plus scale multiplied by direction, this is not gonna work because you can see we kind of expect an int here because of this plus, and it's actually at a 3-element tuple. But what we can do instead is something like this. And magically everything works because we use these custom definitions of operators, which is nice. And in my opinion, this is actually very readable. Kind of, you know that inside these parentheses, you are working with these 3D vectors. So no need to kind of guess what this operator does. Maybe like a little bit of a need to guess what this operator does, but overall, I think that's pretty readable. Okay, fine. Let's move on. So what is happening now is, so this is the aspect ratio of an image that we'll be generating. And I guess like this is the start of this setup. So let's switch to this. Great, so let's define a new function here called ray traced image and do this setup. So aspect ratio, if there's one thing that I wish I could get fixed, it's this completion. It's just completely, it just throws me off. I actually had to disable auto completion in Emacs, where I usually work with OCaml, just because of this. So I'm just gonna do like pretty much one-to-one between this and this. All right, so this is just a stub so that it type checks. Let's continue. So here there's a bunch of description about like what's going on. Not the fun part. So here's the viewport, the camera, and the 3D space. And so here the author defines kind of these vectors that will help us navigate the 3D space. One of the vectors called VU, which is from left to right, and another one called VV, which is from top to the bottom. I'm not sure why it's like U or V here. It's not very, and maybe that's an established terminology. I'm not sure, but I will just probably call it kind of left to right, top to bottom, and that'll be it. So then there's these are the pixels, blah blah blah. Okay, so let's implement these parts. So this is what we already have. Now let's set up the camera. So we have the focal length, and the focal length I think is defined somewhere here. It's basically this distance, the distance between the camera to the viewport. So we have the focal length 1.0. We already have viewport height and viewport width. So we don't need that. Maybe we just need to move it a bit down. So we have the camera center, which is 0.3D. And in fact, we don't need this 0.3D here. This type is just float, tuple of floats. So we could just leave it like that. But I think there is kind of, this gives us a bit more clarity as to what is going on. Okay, so now we have these vectors across the horizontal and kind of vertical viewport edges. So U is going to be left to right. And it's going to be viewport width. So that's in the direction of the x-axis. And then it's going to be 0, 0. Then we have top down. So here it's going to be 0. This is going to be viewport height. And the reason it is negative here is because basically in the 3D space, the coordinates go up like this. So when we go down, we need to just inverse the vector. Okay. All right. Interestingly, this thing actually complains about these unused opens. Okay, so I guess like one thing I would like to do though, then is this function called make, which will take a tuple actually we could just or maybe I don't want to do this right now. Okay, fine. Let's just remove these. All good intentions. Okay, and now we have this part here, which kind of calculates the delta from pixel to pixel. And this delta is this particular distance. So what we need to do is we take this vector, let's say viewport U, or in our case viewport. Okay, let's define it here. Pixel delta left right. So that's gonna be viewport left right. And now let's open vec3d so that we can use the division operator. And we just divide it by the number of kind of pixels in our image. So the same thing for top down. All right, now we calculate the location of the upper left pixel. And the formula is actually very straightforward here. Basically, at least here, we say that the camera, which is at 0, 0, 0, is looking at the center of the viewport. So the center will be at kind of 0, 0 minus focal length. So what we do is we take the camera center. Let's open Vec3D right away so that we can use the operator. So we take the camera center, then we gonna subtract the 0, 0 focal length, which is gonna move the vector from here to here. Okay, then we move it to the left, like half of the viewport size to the left and half of the viewport size to the top. And this actually doesn't look too bad. So here, it's pretty readable. Here it's also pretty readable. I guess like one thing that I don't quite like is having this float of int like everywhere. So maybe what I would do instead is define another operator that will accept not the float, but an integer scalar value. And this is the time where you need to be creative and come up with something interesting. Let's say divide bang. Why not? And what this is gonna do, actually we don't need to deconstruct it here. And we divide it by this. So if we go back here, we can remove this thing and just use this custom operator. All right. Okay, so I think this actually reads very kind of natural, not very different from this C++ version. And mind that we don't have this type disambiguated operator overloading, blah blah. It's just a creative use of opens. All right, so the last thing that we need to do is to define the location of the pixel 0, 0. So let's do this. Okay, so we start with the upper left, then we add half of the delta, and again need to use the open. Pixel delta left right, pixel delta top down. Okay. Looks good. And now when we actually define this render function, what we're gonna do is for every pixel, we calculate its center, we calculate the direction of the ray from the camera to this pixel, we create the ray, and we calculate the pixel color using this ray. Okay, so this looks pretty reasonable. Let's define this function called render. It's going to take a row and a column of a pixel. Then what we're going to do is pixel center is going to be like the 0, 0 pixel. Again, let's open back 3D. Then we add okay, and we probably need another operator here for the multiplication with integer scalars. So let's do it like this. Okay, so we take the row, pixel delta, no, that's not the row, that should be the column. Pixel delta left right, plus row, pixel delta top down. Okay. So we create a ray from camera center to the pixel. Okay. And we just return the pixel. So now we need to stop this function called ray color. It's gonna take the ray and return the pixel. And let's just return black pixel for now. Okay, so that's not quite right. So what we want to do is create a color. Okay, so that's gonna be, and now we want to translate this color to pixel. All right. So far looks good. So let's swap this sample image for a ray traced image. Okay, so this doesn't, okay, this didn't look right, and it's not right because we need to use the render function. What it doesn't like. All right, of course. Cool, so now we have this image, which is 400 by 225 with black pixels, which is exactly what we kind of expected. And now it's time to define this kind of stub function that will just produce this blue to white gradient. And for this, we need to define another function called unit vector. And if we just look for unit vector, what it does, it takes a vector, divides by its length, so that the resulting vector has length 1. That's very straightforward. And we can define it inside vec3d. All right, that's like very straightforward. And here we do the following. And we can deconstruct it right away. And now we need to kind of blend things a bit. So we have this blending factor here, which is 0.5 multiplied by we have this unit direction, and we only need the y coordinate. So we take the y, and now we produce color So we start 1 minus blend factor multiplied by one plus blend factor multiplied by 5, 7, 1. Okay, and look at that, we just got the gradient that we wanted. Yeah, so I guess this is it. That's part 2. Maybe just like a very quick retrospective on the code. So what we have done so far is we have defined this module vec3d, which is basically, it adds some operators for working with 3-dimensional vector of floats. These operators actually, they feel very natural and are quite ergonomic to use. So let's say in this particular example, we have this vec3d, which is the necessary open that brings these operators into scope. And then this reads very natural. So we take the one vector, we subtract another vector, we subtract another vector divided by a scalar value, and so on and so forth. So in my opinion, this is pretty nice. Kind of one thing that is a little bit frustrating is that you need to have these local opens if you want to use these operators. And also when you use these operators, the operators will get redefined. So if you want to do something like, let's say, instead of 2, we might have had something like 3 minus 1. This is not going to work because 3 now expects this 3D vectors of floats. I think we can bring minus into scope like this. No? Oh well, too bad. So I guess like this is just one downside, but other than that, it's not that bad. So I guess in my opinion, this was a pretty kind of straightforward exercise in defining a bunch of operators for working with vectors of floats in OCaml. I think the result is pretty ergonomic to use, and I mean, obviously we'd have to kind of work with this code a bit more, implement a bit more functionality to know for sure like what are the pros and cons, but for now looks reasonably well to me. Yeah, and I guess like one thing I wanted to mention is that in addition to this series of kind of doing this ray tracer in OCaml, I decided to do another one like in parallel, kind of the same ray tracing in one weekend but in Rust, so that we can contrast and compare. It's like doing a thing in 2 different ways is more than 2 times the fun. So let's see how it goes. But for now, thanks for watching. I hope that was interesting. See you next time.